Hello. Hello and welcome to this exemplified read-through of Python Standard Library. We had finished the calendar module. Now we will go and look at the collections module. So this would be very useful and the example will be given at the end of the video. So it might take us probably three videos in all. So without further ado, let's get started with the read through. Okay. Now note that this is a very important module and you can use it in many ways. Okay. Therefore, it is quite important that you pay attention and get as much details as possible. We will do that. So let's get started. This module implements specialized container data types, providing alternatives to Python's general purpose built-in containers. The built-in containers are dict, list, set, and tuple. So this module gives us name, tuple, DQ, chain map, counter, order dict, default dict, user list, and user string. The name tuple is effective function for creating tuple subclasses with name fields. DQ is a list-like container with fast appends and pops on either end. ChainMap is dict-like class for creating a single view of multiple mappings. Counter is dict subclass for counting hashable objects. Order dict is a dict subclass that remembers the order entries were added. Default dict is a dict subclass that calls a factory function to supply missing values. User dict is a wrapper around dictionary objects for easier dict subclassing. User list is a wrapper around list objects for easier list subclassing. User string is a wrapper around string objects for easier string subclassing. So we start with chain map. A chain map class is provided to quickly linking a number of mappings so they can be treated as a single unit. It is often much faster than creating a new dictionary and running multiple update calls. The class can be used to simulate nested scopes and is useful in templating. So the constructor takes maps as an argument. We'll see what those maps are. A chain map multiple dicts or other mappings together to create a single updatable view. If no maps are specified, a single entry dictionary is provided so that a new chain always has at least one mapping. The underlying mappings are stored in a list. That list is public and can be accessed or updated using the map substitute. There is no other step. Lookup search the underlying mapping successively until a key is found. In contrast, writes, updates, and deletions only operate on the first mapping. A chain map incorporates the underlying mappings by reference. So if one of the underlying mappings get updated, those changes will be reflected in chain map. All of the usual dictionary methods are supported. In addition, there is a maps attribute, a method for creating new subcontexts, and a property for accessing all but the first mapping. The maps argument is a user updatable list of mappings. The list is ordered from first first to last first. It is the only stored state and can be modified to change which mappings are searched. The list should always contain at least one mapping. Then we have new child, new underscore child, which returns a new chain map containing a new map followed by all of the maps in the current instance. If M is specified, it becomes the new map at the front of the list of mappings. If not specified, an empty dict is used, so that a call to d.new child is equivalent to chain map with an empty dictionary followed by maps. If any keyword arguments are specified, they update past map or new empty dict. This method is used for creating subcontexts that can be updated without altering values in any of the parent mapping. Then we have parents. It is a property returning a new chain map containing all of the maps in the current instance except the first one. This is useful for skipping the first map in the search. Use cases are similar to those for the non-local keyword used in nested scopes. The use cases also parallel those for the built-in super function. A reference to d.parents is equivalent to ChainMap d.maps one column. Note that iteration order of ChainMap is determined by spanning the mapping for last to first. Suppose we have baseline, which is a dictionary, music is a key, back is the value, art is another key, Rembrandt is the value. Then adjustments is another dictionary. We have art as a key, Van Gogh is the value, opera is key, and Carmen is a value. Then we can send this to ChainMap constructor, and then we pass that to list, and we get keys as a list. The music, art, and opera will be the keys. Art is a duplicate in both of them, so only one will come. This gives the same ordering as a series of dict.update calls starting with the last mapping. Combined is equal to baseline.copy, combine.update, adjustments, and list of combined is music, art, opera. We'll see all this. ChainMap examples and recipes. This section shows various approaches to working with chain maps. Example of simulating Python's internal lookup chain. So from built-ins, we take the dictionary, we pass it to vars, then globals, we put them into chain map. Example of letting it, so you might want to look at it, what it does. Let me execute it quickly. So we take Python and we push this. Okay, we have to import chain map, right? Collections, import chain map. When it becomes file lookup, and there we have everything. Okay. So example of letting user specified command line arguments take precedence over environment variables, which in turn take precedence over default values. So we import OS and argparts. We have not yet looked at argparts module. So defaults are color and user key with values red and just respectively. We create an object of argument parser and we add argument -u or minus video and -c and minus color. So we pass the arguments and then we put them in namespace and we iterate over the variables, okay, or the items of the list. And what we do is that we construct a key with user and color, okay? And then command line args, OS environment, and defaults are passed. And finally, we print combined color and user. Example patterns for using the ChainMap class to simulate nested context. So we create a root context. Then we have child context, D and E from C, and we create a context dictionary, E.maps 0 from this E object and -1. There is the root context, and we have parents. Okay. Then in the D, we set a key X is equal to 1. We get the first key of the chains of context, we delete that key, then we look at all the nested values, we check all the nested values, we find the number of nested values, all nested items, and flatten into a regular dictionary. The ChainMap class only makes updates, writes, and deletions to the first mapping in the chain, while lookups will search the full chain. However, if deep writes and deletions are desired, it is easy to make a subclass that updates keys found deeper in the chain. We create a deep chain map, and we have a set item overloaded function, which takes key and value as the argument. We go through self.maps, got a key in those mappings, we set mapping key is equal to value and return. And over here, we set it in the maps 0, key is equal to value. For delete item, it's the same thing that we create our mapping and then we find the key and delete it. If it is not found, then we raise key error. Okay? So we have a deep chain map of three dictionaries. Then we set lion is equal to orange, snake is equal to red. It's a new key added, and then we delete elephant. And then we construct deep chain map with zebra, black, snake, red, empty dictionary, and lion is equal to orange. If you print the final result. Next, we have counter objects. A counter tool is provided to support convenient and rapid tallies. For example, we have a counter object here. And for word in this list, we count the number of words. And finally, count is, it is a frequency counter. It will print blue is 3, red 2, and green 1. Okay. Now we have another example. We import 3 and we open a file and we read it, right? And we find all the W plus, that is alphanumeric text, and we convert these words to lowercase, and then we see the counter words. We create counter object from words, and most common is the method on the object, and we print the 10. Then we see the tuples with key value there. So there are several constructors. We have keyword arguments, table, and keyword arguments, mapping, and keyword arguments. A counter is a dict subclass for counting hashable objects. It is a collection where elements are stored as dictionary keys and where counts are stored as dictionary values. Counts are allowed to be any integer value, including zero or negative counts. The counter class is similar to bags or multisets in other languages. Elements are counted from a table or initialized from another mapping or counter. We create a counter and we create it out of Galahad, and we have another counter we create it from a dictionary, or we create another counter with keyword arguments. Counter objects have a dictionary interface except that they return a zero count for missing items instead of raising a key error. So we create a counter object out of eggs and ham, and if we look for bacon, it would be 0. Setting a count to 0 does not remove an element from a counter. Use del to remove it entirely. So this won't delete, but this will work. I don't care what's changed in the version. Counter objects support additional methods beyond those available in known dictionaries. So one is elements, returns an iterator over elements, repeating each as many times as its count. Elements are returned in the order first in counter. If an element's count is less than 1, elements will ignore it. So for example, C has count 0, so C was not printed, and D had count -2, so D was also not printed. Then we already saw most common and is equal to none. Return a list of n most common elements in their counts from the most common to the least. If n is omitted or none, most common returns all elements in the counter. Elements with equal counts are ordered in the order first in counter. So we already seen that. Then we have subtract, which can take keyword arguments, it can take a table, and keyword arguments can take mapping and keyword arguments. Elements are subtracted from a table or from another mapping, like dict.update, but subtracts counts instead of replacing them. Both inputs and outputs may be 0 or negative. So we have count here A is equal to 4, B is equal to 2, C is equal to 0, D is equal to -2. Then we subtract, so A, we subtract 1 from A, 2 from B, 3 from C, and 4 from D. So A becomes 4 minus 1, 3, B becomes 2 minus 2, 0, C becomes -3, and D becomes -6. Then we have a total. It computes the sum of the counts. So A is equal to 10, B is equal to 5, C is equal to 0, the sum would be 15. The usual dictionary methods are available for counter objects except for two which work differently for counters. One is from keys and argument is reachable. This class method is not implemented for counter objects. Then we have wait, which has three forms in the same way, like constructor. elements are counted from a table or added in from another mapping or counter like dict.update, but adds counts instead of replacing them. Also, the table is expected to be a sequence of elements, not a sequence of p-value pairs. Counters support rich comparison operators for equality, subset, and superset relationship. Equality, not equal, less than equal, greater than equal. All those just treat missing elements as having zero counts, so that counter A is equal to 1 is equal to counter A is equal to 1, B is equal to 0 returns true. Common patterns for working with counter objects. You can take total, you can clear all the counts, which resets all counts, you convert it to list, which will give us unique elements. So we have set, which will convert it to set, dict will convert to a regular dictionary, items will access will give us element and counts. Counter dict list of pairs will convert a list of element counter pairs, and most common will give us least common element. So this is what you need to do. And plus C will remove zero and negative counts. Several mathematical operations are provided for combining counter objects to produce multisets. Counters that have counts greater or zero. Addition and subtraction combine counters by adding or subtracting the counts of corresponding elements. Intersection and union return the minimum and maximum of corresponding counts. Equality and inclusion compare corresponding counts. Each operation can accept inputs with signed counts, but the output will exclude result with counts of 0 or less. So we create an object C with a count of A3, count of B1, and then we create an object D with count of A1 and B2. When we add, the counts get added. A has now 4 and B 3. If we subtract, then count of A becomes 2 and B is negative, so not shown. Then we do intersection. So we get minimum of C and D. So minimum is of D, A is 1 and B of C is 1. Then we have union, which will give us the max. Then we have equality, so counts are not equal, so it is false. Less than equal to for C, less than equal to D is false. Unary addition and subtractions are shortcuts for adding empty counter or subtracting from an empty counter. So when we do plus C, we get A is equal to 2, and when we do minus C, then the count of B becomes 4. Counters were primarily designed to work with positive integers to represent running counts. However, care was taken to not unnecessarily exclude use cases needing other types of negative values. To help with those use cases, this section documents the minimum range and type restrictions. The counter class itself is a dictionary subclass with no restrictions on its keys and values. The values are intended to be numbers representing counts, but you can store anything in the value field. The most common method requires only that values be alterable. For in-place operations such as C key plus is equal to 1, the value type need only support addition and subtraction. So fractions, float, and decimals would work and negative values are supported. The same is also true for update and subtract, which allow negative and zero values for both inputs and outputs. The multiset methods are designed only for use cases with positive values. The inputs may be negative or zero, but only outputs with positive values are floating. There are no type restrictions, but the value type needs to support addition, subtraction, and comparison. The elements method requires integer counts. It ignores zero and negative counts. Next is we have DQ objects. I think we will cover this in the next video. I will end this video here. And in the next video, we will start from DQ. So we have covered Tulna, ChainMap, and counter. Okay. So DQ is where we will start. And I hope that in 3 videos, we should be able to finish this, or maybe 4 for example and all. It depends how we go about it. So I hope that you are enjoying this read through of standard library and finding it useful for learning Python. So I thank you for watching the video, and we will meet again in 4 days with another video on Python standard library covering the remaining of container classes. So once again, thanks a lot for watching the video. keep learning. I wish you all the very best. And I'll see you in the next one. Have a nice day and bye.